Hi, let's continue our discussion on evaluation metrics. By the end of this topic, you will be able to form an accuracy matrix to explain the results of a classification model. Let's start with the simplest and the most widely used among these, which is accuracy. Accuracy can be simply defined as the correct predictions upon the total prediction. Easy, right? Let's try to formulate the accuracy using the confusion matrix. I hope you remember the 2x2 confusion matrix that we discussed in the last video. Looking at the confusion matrix, the number of total correct predictions will be the sum of true positives and the true negatives. On the other hand, the total predictions will be the sum of all the predicted values. Therefore, the formula of accuracy now looks as follows. But let me ask you something. Does a higher accuracy value mean a higher performance model? Obviously, the higher the accuracy, the better the model. This was pretty simple, right? To understand the purpose of my question, let's look at an example. Suppose there's a group of 500 people who undergo a cancer diagnostic test. 6 patients are tested as positive, which means they have cancer, whereas the other 494 patients do not have cancer. Intuitively, we can say that the patients suffering from cancer are pretty less in number as compared to the people who do not have cancer. This is a classic example of imbalanced data. Now, what is an imbalanced data, you may ask? An imbalanced data is a data set which has disproportionate numbers of either positive or negative classes, and both the classes are not equally or nearly equally distributed. For example, here the class 0, that is, people who do not have cancer, is far more frequent than class 1, that is, people with cancer. Most of the logistic regression problems suffer from this problem of imbalanced data, and you need to be mindful of the same. Now, our job is to build a predictive model that can predict whether a patient has cancer or not. This model would take inputs such as age, gender, previous history, tumor size, tumor color, among other things. Let's assume we have built the model and have a confusion matrix ready as shown on the screen. Take a moment to parse through this. What's your first reaction? There are some big values and some small values in the confusion matrix. The first intuition would be to calculate the accuracy of our model. Just plug in the values into this framework we defined earlier. The accuracy comes out to be 98%. Looking at the model accuracy, we can easily conclude that the model we made is performing extremely well, right? Well, not quite. If we look at the confusion matrix of the dumb model, it would look something like this. Let us now input the values from the confusion matrix into the formula for accuracy. The accuracy comes out to be 98.8%. What just happened? How did a dumb model manage to trump a predictive model? We simply used the way of brute force to predict every patient as negative, or maybe the predictive model as we trained is worse than the dumb model. In reality, using accuracy as an evaluation metric on unbalanced data is not a great idea, as we saw in this example. In order to evaluate the classification model properly, we need to look closely at the confusion matrix to find better alternatives to accuracy. We will discuss one such alternative, that is precision and recall, in the next video.